Howdy, it's been quite a while since I posted, and the world has changed in the interim. For one thing, tail fins are no longer popular on automobiles. I confess, I didn't see that coming. But give me a break. At least my last video wasn't a silent movie. I'll try to post more frequently, and I may start looking for stories to tell about advancement in science. Not just of the dry science, but of the human meaning behind achievement. If that's something you'd like, please click the subscribe and bell icons. I've also got something to say about the law of cosines. We should dive into that at some time too. In this episode, we're going to look at energy, how it is relative and not absolute, and how relative energies still add up like they should, even if at first glance they don't appear to. And now, our feature presentation. On this day comes to us the most likable, friendly alternative thinker I've met with a challenge. Ryan Vincent postulates there's something amiss with kinetic energy if the world is in motion, rotating, or moving in space. He's got a very interesting springboard for thought experiments. I respectfully disagree with his conclusions, but must offer gratitude for his challenge to conventional thinking. Ryan, if you're out there, please let me know if I get anything wrong. Please also allow me the use of some very simple math because your observations involve quantities of kinetic energy. If we don't use math, we're reduced to saying things like, Fred's got a whole bunch of stuff, but Barney's got a whole bunch more. If they both jump off a cliff with their stuff, Barney's going to make a bigger thump. True, but more satisfying if we add in some quantities and observe proportions and relationships with precision. Here's the quandary. If I hurl an overweight 8-kilogram black swan to 5 meters per second, he ends up with a kinetic energy of 100 joule. For the sake of discussion, I accelerated the ducky at a rate of 16.67 meters per second squared for a distance of 0.75 meters, applying a force of 133.33 Newton. Three ways to calculate that kinetic energy come to mind, and there are likely more. We could look at 1/2 mass times velocity squared, which comes to 100 joule. Or we could look at the mass of the ducky times the distance force was applied times the acceleration, which comes to 100 joule. Another way, we could look at the classic definition of work as force applied over distance and get, there's a pattern here, 100 joule. That there are many paths to enlightenment does not mean enlightenment mutates by path chosen. Now let's launch the duck again. He's got protective gear because we don't harm critters here. This time we'll use a precision duck cannon and zap him up to 100 meters per second. For 1/2 mass times velocity squared, he's got a KE of 40,000 joule. Launch him again at 105 meters per second, he's got a KE of 44,100 joule. Adding 5 meters per second added 4,100 joule. Now comes Ryan's conundrum, which I can solve. If I'm in a boxcar on a high-speed train, if I pitch the duck at 5 meters per second relative to me, I observe he's got a KE of 100 joule. Does that mean the train is standing still? No. But wait, you say. If the train is moving 100 meters per second and you added 5 meters per second, his real-world velocity is 105 meters per second, and his KE has to be 44,100 joule, not a paltry 100 joule. This is as wrong as oil rigs in a bird habitat. But it's not wrong. The ducky in my moving frame of reference is 100 joule, and his KE against the ground is 44,100 joule, and that adds up perfectly. It takes me 100 joule to accelerate the duck you see at 100 meters per second to what you see as 105 meters per second for a gain you perceive of 4,100 joule. That works because of teamwork. There's no I in team, but in this case, there's a little bit of the train's diesel fuel. To understand the duck's kinetic energy, you have to account for all the chicken nuggets in the Happy Meal. So there I am in a boxcar moving 100 meters per second with a nervous duck. Once again, I hurl the little fellow at 5 meters per second and observe his KE is 100 joule. But let's look at what it took to do that. I pitched him with a motion of 0.75 meters with my arm, applying a force of 133.33 Newton over a duration of 0.3 of a second. That means I pushed back against the train's motion with a force of 133.33 Newton. To maintain constant speed, the the train had to generate an equal 133.33 Newton for that same 0.3 of a second, during which time it covered 30 meters. Work is force over distance, so that accounts for 133.33 Newton over 30 meters, or 4,000 joules. The observer on the ground insists the duct gained 4,100 joules. Sure enough, the train's 4,000 joules required to maintain speed, plus the 100 joules I added to get the ducky up to 105 meters per second over the ground, adds up. So, Ryan, I believe kinetic energy measurements can't reveal constant motion. If that's not enough, consider a jet cruising at 800 kilometers per hour. Walk forward in the aisle at half a normal relaxed walking speed, which I would say is probably 1.6 kilometers per hour. If kinetic energy were absolute and you didn't have the help of the aircraft's engines and momentum, you had to add enough kinetic energy to accelerate yourself on a bicycle from standing still to 50 kilometers per hour. Does initiating a slow walk in an airplane aisle seem like as much work as accelerating a bicycle to 50 kilometers per hour? If not, you're seeing how energy is indeed relative. Thank you for watching. I sincerely thank Ryan for challenging me to learn about kinetic energy. I think he came to incorrect conclusions, and I believe physics is on my side. It's a win-win for all since we learned something, and physics is never the least bit upset about hypotheses that end up falsified. It's all part of advancement, and physics these days is very mature. Now, back when physics was a whippersnapper, say 10 to the minus 43 seconds after the Big Bang or so, it might have been hurt by wrongful thought experiment allegations. These days, though, falsified theories roll off physics like water off a swan's back. No harm, no foul. Be well, be safe, and I'll see you the next time around.